Hi, this is Richard Averitt. I'm a professor in physics at UC San Diego, and today I'm going to tell you a little bit about dynamics and control in quantum materials. And so this is a really exciting and emerging area where we're looking at a host of different quantum materials, and we're using many different ways to try to manipulate and control their properties on demand. And what I'm going to focus on today is how we're doing that with short pulses of light. So what I'm going to do now is turn off my camera and get started on going over some of these slides that talk about this idea. Okay, so basically this idea of properties on demand in quantum materials, as I mentioned, is a very rich area. And the idea is that we can take various materials, our properties of materials, and they're very sensitive to different types of perturbations. We could be talking about superconductivity, metal insulator transitions, charge ordering, orbital ordering, topological properties. And the idea is that we can come in with different techniques, perhaps a magnetic field, we can manipulate the properties of that quantum material. We can also do things like use photoexcitation to create metastable states. There's just a rich panoply of possibilities to manipulate these materials that are sensitive to perturbations. And you can learn a little bit more about that in these papers here, but what I said is I'm going to focus on basically how we do this with light for the most part. And so this brings us to this idea of photon-based dynamics and control in quantum materials. And the idea is quite simple. We take some short femtosecond pulse lasers. I'll tell you a little bit more about that in a second. And we have one pulse that we call the pump pulse, and it initiates a change or drives dynamics in a system. And then we come in with a secondary pulse that's delayed in time with respect to that pump pulse to interrogate what has happened. And so we might measure a change in reflectivity or a change in transmission, and we can map out those dynamics. And the evolution of those dynamics, we could see some interesting things such as new properties emerge because of that photoexcitation. Okay. One of the things that's really happened in the past few years in photon-based dynamics control in quantum materials is that there's been a lot of advances in lasers, and so we can do a lot of interesting things now, which means create short pulses that can be used to pump or drive material, a quantum material, with various different wavelengths. For example, we might use far infrared or terahertz pulses, and you can have things like Zener tunneling or carrier acceleration that can drive novel dynamics. A really particularly exciting area is with the generation of mid-infrared pulses, we can basically drive phonons coherently, and there's this whole interesting area of nonlinear phononics. I'll say just a little bit more about that later. Another possibility is to dynamically drive magnons in various materials, and of course we can also do excitation in the visible to drive things like charge transfer transitions and maybe manipulate the properties by initiating dynamics with a pump pulse such as that. What's really neat about this, and we're still trying to figure out what we can do in terms of this on-demand control in quantum materials, is to answer questions of are these pump pulses mode selective? And the answer is yes, but to what extent? And what do I mean by that? Well, you want to pump a specific degree of freedom, and can you do that by the appropriate choice of wavelength? Are there multiple pathways to the same photoexcited state? That's a question that we're still trying to answer. And probably the most exciting thing is are there unique states that are accessible through the choice of the photon energy? So that's another important concept that we're investigating. Now that was the pump, but the other thing that's happened is there's been an explosion in the past 10 years in terms of the ability to probe dynamics in quantum materials. And again, the idea here is that we now have this ability to generate pulses across this whole large swath of electromagnetic spectrum, and so we can probe dynamics that were initiated by a pump pulse with pulses in the terahertz or the mid-infrared, using photoemission, using X-ray sources. And so the idea here is that if you look in the spectrum, you can see there's all these different excitations that are accessible, and so that allows us to really try to understand the dynamics that we've induced in a material with these short pulses. Okay. Now within my lab, we're doing research on quite a number of different materials. I'm certainly not going to talk about all these today, but we're looking at a lot of different transition metal oxides. And some of the sorts of things we're doing is we had one example where we were able to photoinduce essentially using light metastable phase transition from essentially a charge-ordered antiferromagnetic insulator to a ferromagnetic metal. That's something that we're still investigating. Another area that we've been doing work on is trying to manipulate and control superconductivity with light. And we have some evidence that we've been able to do that using short pulses of light. Another area that we're very interested in is this idea of integrating little metamaterials, basically little sub-wavelength circuits with quantum materials, and trying to look at the coupling between these resonators and the quantum material on which they're placed upon. And then the last example, and the one that I'll actually talk about today in a little bit more detail, is this idea of dynamics controlling antiferromagnetic Mott insulators. Mott insulators, of course, are the parent compound of a lot of interesting materials, such as superconductors or materials that exhibit colossal magnetoresistance, such as these. But the one I'm going to talk about today is a gadolinium titanate, where we do photoexcitation, and we're looking at how it might be possible to use light to manipulate the magnetization in this particular system, which is, as I'll discuss in just a minute, a ferromagnetic insulator. Okay, so as I mentioned, we've really we are currently actually looking at a lot of different quantum materials using this idea of light-based manipulation. But the one I'm just going to talk about today is really this idea of moving towards optomagnetic control of the ferromagnetic insulator gadolinium titanate. And one of the things I'll show you is that we can see interesting spin dynamics, and we also see spin-enhanced coherent acoustic phonons. And so over the next few minutes, let me just give you a little bit of a feel for this and tell you some of our results. I won't go into excruciating detail, but I'll at least try to give you a feel for some of these exciting ideas that can be investigated using femtosecond pulses. And in this particular case, we're going to actually do it in a magnetic field. Okay, so this is a very interesting and rich area, and it's this area has been termed Optospintronics. Here's a nice review paper that came out in 2018 on antiferromagnetic optospintronics. And there's a lot of interest in looking at dynamics and antiferromagnets. The idea being that if you can manipulate spins and antiferromagnets, that's actually quite interesting because you can do it on a much faster time scale potentially than in ferromagnets. And this review article talks about some of the ideas here, and this is just a couple of examples just to kind of give you a feel for things. But this is an example where in nickel oxide, where there's a magnon at terahertz frequencies, and you come in with a short terahertz pulse. This red pulse has this spectral content shown here, and you basically coherently ping that magnon just as though you were ringing a bell. And then using Faraday rotation, you can see this really long precession of the antiferromagnetic degree of freedom in the system with the Kerr Faraday rotation. And then here's another example where they use circularly polarized light to drive magnetization dynamics, where essentially the circularly polarized light acts as an effective magnetic field. And so this is a very exciting area that's rich with numerous possibilities, and this extends to other ideas that have been developed. And so there's these kind of exciting ideas of light based on demand control, of magnetism based on nonlinear phononics and flow K engineering. These two papers are a couple of theory papers that give the idea, specifically in the titanates, of how to manipulate potentially manipulate the magnetism in these systems by driving phonons. And the idea of nonlinear phononics can kind of be captured in this little image here that's from this paper, where you come in with a short pulse of light. This blue is given by the pulse envelope, and it's in the mid-infrared, and it will drive a specific infrared active phonon, and that infrared active phonon is coupled to a Raman active phonon. And so this infrared active phonon, the oscillations are given in green, and this drive this coherent Raman phonon, and so you have these oscillations. But in addition to that, you get what you might call a rectification of the lattice, and so this change in the lattice structure by this coherent phonon excitation can thereby change the properties of the material. So this idea of you manipulating the lattice and thereby the properties of the materials using coherent infrared pulses is really an exciting idea. Another exciting idea is this idea of what has been termed flow-K engineering. In this case, you could think about this in a simple way, is that you're actually going to use non-resonant pulses, and the very existence of that light on the system, you have this on a given material, you have this enhanced light matter interaction, and you might be able to do things like, by applying an electromagnetic field, modulate the exchange interactions in a solid. And for example, this little U here, I'm not going to go into the details, has the electric field in it, and so you really literally, during the time that the pulse is present, you modify the exchange interactions. And so this shows a plot of the photon energy as a function of the field energy taken from this paper. And you can see that you actually, by choosing the right wavelength and the right field strength, you can actually manipulate materials and have them potentially go from being ferromagnetic to anti-ferromagnetic, or vice versa. Okay, so that idea is explained in this paper here, and this is also particularly relevant to the titanates. Okay, these are really neat ideas. They are, I would say, challenging, but we're beginning to try to work on these things to see if we can make some headway. And so the material that we've been looking at is this gadolinium titanate. As I mentioned, this is a ferromagnetic insulator, has a transition temperature of about 32 Kelvin. Now, the the titanium 3+ spins, they're ferromagnetically aligned along the c-axis, and they're anti-ferromagnetically coupled to the gadolinium. And the gadolinium has this huge moment of 7 Bohr magnetons, and whereas the titanium, this 3D1 orbital, basically has 1 Bohr magneton. And since they're anti-ferromagnetically coupled, when you saturate the magnetism, you have 6 Bohr magnetons, just 7 minus 1. So this is a really interesting, the titanates are a really interesting class of materials, and you can kind of see this in this phase diagram here, where the rare earth ionic radius, as you change that, you can see this is the rare earth ionic radius here, and this is for different compounds. So if you have lanthanum, for example, you actually have an anti-ferromagnetic system with a nail temperature of about 120 Kelvin. And as you change that ionic radius by changing that rare earth, you see that you kind of get into this region where you have a crossover from anti-ferromagnetic behavior to ferromagnetic behavior, and that's shown here. And this is all based on the fact that the tolerance factor are really, if you want to think about it, the lattice distortions, the octahedral tilts and rotations are changed by this substitution of the rare earth. And in particular, the gadolinium is pretty interesting because it's kind of right on it's as close as you can get without doing, basically doping, non-stoichiometric doping. But with the gadolinium, it's about as close as you can get in terms of being between this ferromagnetic and anti-ferromagnetic region. And so the idea is, okay, well, this particular material might then, since it's right on the boundary of these two different phases, be particularly amenable to manipulation, say by phonons or by flow-K engineering, as I mentioned on the previous slide. So we've gotten single crystals of this material, and we've been starting to investigate its magnetic properties. And so this, what I'm going to tell you about now, is this paper that was recently published on magnetoelastic coupling to coherent acoustic phonon modes in this material. This is a nice collaboration that was led by a student in my group, Dylan Lovinger, who's now graduated. And it's a collaboration with people at UC Santa Barbara, from where we got the crystal and also some theoretical input, and then also Soon J. Moon, who helped us do these optical conductivity measurements that are shown right here. But the idea is the following. In this particular case, we're not really ready to do the phonon drive or the flow-K drive. We kind of want to just begin to understand what are the magnetization dynamics in the system. So what we did is we came in with a short pulse that basically does an excitation across the Mott-Hubbard gap, as shown here, with 1.8 eV pulses. And we know that that's the case because of these optical conductivity measurements here. So basically, we're exciting right here where we have this as I said, Mott-Hubbard excitation for these T2G bands from the lower Hubbard band to the upper Hubbard band. And so we're going to photo excite that transition, and then we're going to look at the dynamics. But we want to do this in a little bit more careful way. So we did these measurements with the experiment that's shown here. I'm not going to go into all the details, but essentially we're measuring the photo-induced changes in reflectivity. We call this delta R over R, and also the polar Kerr rotation dynamics of this gadolinium titanate. This shows an example of our setup. So we have an OptiCool magnets capable of going down to 1.5 Kelvin and up to 7 Tesla. And we have, a whole host of lasers that we use to generate those pump pulses I was telling you about earlier, and these probe pulses. And we can just bring it into a conventional cryostat, or with a couple of flipper mirrors, bring it into the OptiCool. And in this particular experiment that I'm going to show you, at least for the Kerr rotation dynamics, we actually came in through the top where the magnetic field is oriented perpendicular to the surface of the optical table. And we came in at normal incidence with our pump and probe beams, near normal incidence. And so we're doing what's called polar Kerr rotation measurements. And so this really gives us a lot of access to be able to very carefully investigate these pump probe dynamics as a function of both temperature and magnetic field. I'm going to show you some of these results now. The first experiments we did were photo-induced changes in reflectivity. I'm not going to spend a lot of time on these, but I'm just going to point out a few interesting things. This is the photo-induced change in reflectivity. You get a change of about, maximum change on the order of, 2 times 10 to the minus 2. And what's shown here is the dynamics as a function of temperature. This temperature scale here also maps onto the dynamics shown here. So this is a change in reflectivity as a function of time. And near room temperature, you just see exponential decay. And then what's interesting as you go to lower and lower temperatures, you start to see a much larger signal and much longer dynamics, both in the rise time and then also in the decay time. In particular, the dynamics become extremely slow right at the transition temperature. This particular curve here corresponds to, I think, about 30 Kelvin. So that's right in the vicinity of TC. Without going into too much details, we've just plotted the peak change in reflectivity at 500 picoseconds as a function of temperature, and you see this large increase, and we've actually fit it with something that would be consistent with essentially having a magnetic signal. Okay, a delta R over R measurement is not a measure of the magnetization dynamics, but this is certainly telling you there's something that's happening right when you get into the vicinity of the transition to the ferrimagnetic ordered state. And one other thing I'd like to point out that you can't see too clearly here is that there's also some weak oscillations on top of this data. These are what are called coherent acoustic phonons. I'll come back to that in a couple of minutes. Actually, I'll come back to that on the next slide. I'll just show you real quickly some of the dynamics. I'll just break these dynamics down just a little bit more for you before we go into the Kerr measurements. And so the photo-induced reflectivity dynamics, what happens is a lot of new dynamics emerge when we get into that ferrimagnetic order state. And this is just kind of a cartoon showing you some of what can happen. Above, well, out of the magnetically ordered region at 100 Kelvin, you just see these little oscillations, and you see essentially a fast exponential relaxation with a long time offset. It's very short, picosecond time scale is just what we call electron phonon relaxation. That initial electron distribution that was excited is thermalizing with the lattice via emission of phonons. But what's interesting is when you get into that ferrimagnetic ordered state, all these new time scales, which correspond to new dynamics, pop up. So we see things related to electron-photon coupling that I already mentioned, orbital ordering dynamics, spin lattice ordering dynamics, and other sorts of dynamics. Okay, and so the basic idea here is new dynamics emerge upon approaching TC. And the one thing that is interesting, remember I mentioned these little wiggles. We've extracted those, and I'm showing that on this curve here. And you have to look at this a little bit carefully. This is the change in reflectivity as a function of time at these different temperatures. And these kind of reddish curves are all well above the transition temperature, and you kind of see this coherent oscillation Okay, it's a little bit chirped and it has some interesting features, but it doesn't change so much. But then what happens is when you start to get into the magnetically ordered region, you see that amplitude increases by quite a bit. And so this really shows that these coherent acoustic phonons basically are enhanced once you get into the spin ordered state. Okay, so there's all these suggestive things that are occurring in these reflectivity dynamics, but as I mentioned, these are just suggestive that interesting dynamics are occurring as you approach the magnetically ordered state in this ferrimagnetic insulator. But to really then look at that in more detail, you have to go do a magnetization measurement. So that's what I'm going to show you on the following slides in terms of these polar Kerr rotation measurements that we did in the magnetic field using the OptiCool. Okay, so now I'm just going to describe to you these polar Kerr rotation dynamics. These are the measurements where we basically measure the, the photoinduced change in the polarization rotation, and for Faraday and Kerr rotation, this is proportional to the changes in the magnetization. Again, we are measuring the change in the rotation that's caused by doing this photoexcitation. And the way we do these measurements, actually, what's shown in all this data here is we do the measurements at plus H, plus magnetic field, and we subtract off the measurements that we do at equal and oppositely directed magnetic field. And this way you can ensure that you have true magnetization dynamics. So what I'm showing you here is that photoinduced change in Kerr rotation. This is sitting on top of, we measure the static Kerr rotation. This is the change about whatever value you're at a given temperature. So this is, again, the change in the Kerr rotation. And so what I'm showing you here is the photoinduced change in Kerr rotation as a function of time at various fields. This data here is at 0.1 Tesla, this is at 0.25 Tesla, this is at half a Tesla, and this is at 1 Tesla, and we did this for various different temperatures. So let's look at this data a little bit, and we'll actually start considering at low temperature. So if we look at the low temperatures, what we see is an increase, this positive, this delta theta corresponds to an increase in the magnetization. Then as you go to up to close to TC, you now see that you have first an increase in the magnetization and then a decrease in the magnetization. And the closer you get to, in the vicinity of TC or slightly above it even, the sooner you have that crossover from an increase in magnetization to a decrease in magnetization. Now what's interesting is then when you go to a higher magnetic field, you see similar dynamics. The amplitude is increased a little bit. But you again see this behavior that when you get close to TC, there's this crossover from an increase in magnetization to a decrease. And that time gets pushed out further. That's a little bit more pronounced here at the half Tesla data, where now you can see that the crossover from an increase in magnetization to a decrease occurs at something like 400 picoseconds. And then when we get to this highest field that we used in this particular experiment of 1 Tesla, we see that this polar Kerr rotation signal, this photoinduced change, is always positive. So there's always an increase in magnetization. We never see at any time or at any temperature a decrease in the magnetization. So this is actually quite interesting, and we think we have at least a preliminary interpretation of that, and I'm showing you that on this slide. This is again the same data I just showed to you a second ago. So this is just a little cartoon to give you some feel for what is possibly going on, where we have the applied magnetic field along the axis of this crystal, and then at t equals 0 we come in with this short pulse of light. And remember, this excitation is across the Mott-Hubbard gap, and so it really is a T2G to T2G excitation. So you're really kind of driving the initial dynamics in the titanium channel. And so at short time scales, really you've put the energy into the titanium orbitals, and so the first thing you could have is basically photoinduced changes in the magnetization of the titanium. And remember, the gadolinium moment shown by these blue arrows and the titanium by the red arrows are antiferromagnetically coupled. So what that means is if you reduce the moment of the titanium along the a-axis, you're essentially going to have this situation where, like what we see at low fields, where there's first an increase in the magnetization, followed by a decrease in the magnetization when energy that was initially in the titanium spins then through some sort of spin lattice coupling or exchange interactions gets into the gadolinium. Okay, so that would account for this fact that at first in this region here you see this increase in magnetization as you decrease the titanium moment, but then you finally get an overall decrease in the magnetization when you start to decrease also at longer time scales the magnetization associated with the gadolinium moments. Now, this is also consistent with this idea that when you get to higher fields, you see this same sort of behavior at first, but now with these higher fields, the gadolinium moment is really kind of much more rigidly aligned along the applied magnetic field. So you only see an increase in the magnetization associated with essentially the decrease of the titanium moment along the h-axis. So this is kind of the idea that we kind of see this coupling between the gadolinium and the titanium moments in these polar Kerr measurements, and this is just something that you would not be able to interpret from the delta R over R measurements. And the ability to have this magnetic field to kind of look at this very carefully as a function of applied field is very important in terms of being able to understand what the Kerr rotation dynamics tell us about how the magnetization of the system evolves. And one of the things you can also see on this data again is you still see these coherent oscillations associated with coherent acoustic phonons. And so we extracted also this coherent signal from the Kerr rotation dynamics. And you see very similar behavior as what I showed you in the delta R over R. And this is interesting because this is in the Kerr rotation. And again, well above the transition temperature, you see kind of these coherent phonons that become much more pronounced and enhanced when you get into the ferromagnetic ordered phase. And so this really shows you basically that these coherent acoustic phonons, in the Kerr signal, that really provides definitive evidence of magnetoelastic coupling. And overall, these Kerr dynamic measurements have provided us some interesting information about the coupling between the titanium and gadolinium spins. And so this really sets the stage now that we have a understanding of what happens when you change the magnetization of the system in terms of what the Kerr signatures are. This really sets the stage for doing measurements like these phononic or flow K magnetization studies, which are somewhat harder, but now we have some better understanding of the material, so we're well prepared to go and try and do those measurements. And so I think this is just one example where you have to very carefully plan the experiments in a stepwise fashion to go towards these really exciting ideas, which is where we're headed. Okay, so that brings us to the end of this presentation. I thank you for taking the time to listen to it. And so really in summary, I hope I showed a little bit about this idea that light-based dynamics and control really provides a fertile ground for exploring quantum materials and really non-equilibrium dynamics in these really fascinating materials. And so in gadolinium titanate, I showed you that we observed spin dynamics exhibiting clear signatures of gadolinium titanium coupling, and we also saw through this Kerr measurements that there's clear magnetoelastic coupling that's manifested in this changes in the coherent acoustic phonons when you hit the transition temperature with the spin ordering. We've been doing other measurements in a magnetic field using the OptiCool, and we have some really interesting results on both topological and Kitaev quantum materials. So we're very excited about those, and we're trying to understand what we've measured, and so hopefully in the not too distant future I'll be able to make another presentation to inform you of what those results are. And so thank you for your time.